Alright, in the second worksheet for 3.1, we're going to see some applications we had seen in 2.6, except we'll be using the basic rules, so it'll go a lot quicker now. To find the equation of a tangent line, what we had seen in chapter 2 was we needed to use y minus y1 equals m times x minus x1, but to get m for this curve, we need the derivative. And back in the last chapter, we did it the long way, but now we have an easy approach. Find f prime, use the power rule. 3 comes down, x raised to 2, minus the 2 comes down, 4, 2 times 2 is 4, x raised to 1, constant's derivative is 0. But this is not the slope yet. This is just a rule that leads to the slope. This gives you the slope at any point, but we need the slope at this particular point when x is 2. So this x value will get substituted. F prime at 2 is 3 times 2 squared minus 4 times 2. That's 12 minus 8, which is 4. So this is going to be our m. M has to always be a constant. Okay, so we'll go back here, and we get y minus y1 is right here. Y minus 3 equals m, which is 4 times x minus 2. If you leave it in this form, I will give you full credit. On WebAssign, you may have to solve for y. Just add the 3 over and type it in, and that'll be fine. I want to demonstrate how this looks on the graphing calculator, so I'll go and type in x cubed minus 2x squared plus 3. Do a standard window. And there's your cubic graph. And I'm going to go to y equals and type in this equation that we got of the tangent line. That's 4 times x minus 2. Then I'm going to add the 3 over to get y by itself. If I push trace and type in 2, it takes me there, and that's the tangent line to the curve. Alright, so it worked out. It checked our answer. For the next question, we're looking at some applications here. So the velocity, it's saying, in centimeters per second of blood r centimeters from the central axis of an artery, if this is an artery, is given by this formula. Okay, v is velocity, little r is the distance from central axis to that wall, whereas r, the capital R, is a radius of the artery. It's from right from the middle, whereas little r is from any other location. So if you think about blood flowing through a blood vessel in a human being, if the artery walls get pretty thick, then the blood can't go as fast, and then that leads to a heart attack. So we're looking to understand how the velocity works in different locations, and we'll interpret our results. So in this case, k for this particular person is 1000, and capital R, the radius of the artery, is 0.2 centimeters. So we need to find v at 0.1. and then we need to find v prime at 0.1. So let's plug in k, which is 1000. Big R is fixed. It's 0.2 squared. Little r is that. So it's 0.1 squared. And you can use a calculator to figure out what that is. So that's 1000 times 0.2 squared minus 0.1 squared. I get 30. So the velocity in centimeters per second of the blood, which is, if this full distance is 0.2, but you're somewhere over here closer to the wall, the blood is going at that rate. Okay? Now, if you played around with this a little bit, if we were looking at 0.2 itself, right in the middle, then you would notice that you get 0. That means that the velocity of the blood in the middle isn't that fast. The closer you get to the wall, there's more pressure and it's going faster. Well, 0.2 would actually be right at the end. Okay, because that's the distance from the central axis. So the wall would block it. To find v prime, we need to first look at v of r. K is 1000. That is fixed. Big R is fixed. 0.2 squared, and little r is a constant, so we won't plug anything in. If you want to clean this up by distributing the 1000, you can, just to make it easier to take the derivative. So that this would be 40 minus 1000's r squared. So b prime at r, the derivative of 40 is 0, minus the 2 comes down, 2000 r raised to 1, and then we plug in 0.1. So that would be negative 200. We plug in 0.1 for r. So this would be the change in the velocity over time. Okay, so to interpret your result, you would say the velocity when little r is 0.1 is 30 centimeters per second and is changing at this rate, at the rate of negative 200. Now the units for this is interesting. It's centimeters per second squared, because you're really looking at the next level. Okay, so the units will make more sense when we get to a different section in this chapter. Now we're going to make a list of words that imply that you need to do the derivative. If you see the word slope of a curve, you need to take the derivative. Okay, if you see the word find the velocity, you need to take the derivative. If you see rate of change, instantaneous rate of change means derivative. And let's see, if you see the word speed, you're going to find the derivative. We may have to add this other words to this list as we move on, especially when we get to business examples. Okay, something else to add to our list is if you see the phrase how fast something is changing, how fast and a quantity, how fast is changing, that tells you that you need to take the derivative. Let's try the next example. A study prepared for a Sunbelt town's Chamber of Commerce projected that the town's population in the next 3 years will grow according to this model, where P of t denotes the population t months from now. How fast, we'll underline that word, will the population be increasing 9 months and 16 months from now? So how fast, meaning you need to first find P prime of t. Now that we have a shortcut, it should be pretty quick. The derivative of constant is 0, plus constant multiplied, the power comes down, so it's 30 times 3 halves, times t raised to 3 halves minus 1, which is a half, plus the derivative of 20t is just 20, because that's a linear piece, that's the slope. If you want to clean this up, you can. You get 45t to the half plus 20. Then we'll plug in 9 months, so it's 45 times 9 to the half plus 20. You can use the calculators. That's the square root of 9, which is 3. 45 times 3 plus 20, you get 155. P prime at 16 is 45 times 16 to the half plus 20, so that's square root of 16, which is 4. 45 times 4 plus 20, and getting 200. So this is how fast the population is changing at 9 months, 16 months. It's growing pretty fast. But the next question is saying, what will the population be? So you don't need the derivative now, but you need the population itself. So you need to go to the original function and find P at 9 and P at 16. So we'll use our calculators. 50,000. 50,000 plus 30 times 9 raised to 3 halves, which is 1.5, plus 20 times 9. Okay, so plugged in 9 here and here. I'm getting a huge number, 50,990. So when time was 0, if you plugged in 0, it was 50,000, but 9 months later it grew and you had that many people. Now I'm going to replace all the 9s with 16s. I need to insert a 1 there and a 6, delete that 9, and then change that 9 to 16. So I get 52,240. Alright, I hope that makes sense. That's the number of people. So moving on to the next question, we have the altitude of a rocket, t seconds into flight, is given by that's the position or the height of the rocket. we need to find an expression for the rocket's velocity to see how fast it's going. Velocity in our list, that means we need a derivative. So velocity is s prime, take the derivative, 3 comes down, negative 6 t to the second power, 2 comes down, it doubles that, so it's 228, t raised to 1, that's linear, 480, constant's derivative is 0. So this is the velocity for any time t. Now we need to compute the velocity of the rocket when time is 0, 20, 40, and 60. So basically we plug in 0 first, so we'll find v of 0, then v of 20, v of 40, and v of 60. You could make your life easier by going to y1, I'm going to clear these other guys, and type in this velocity, negative 6t squared, or x squared, plus 228x plus 480. And go to the table and type in 0, 20, 40, and 60. And that makes the substitution a lot faster. So it's 480, 2640, 0, negative 7440. Let's think about these answers, because we need to interpret our answers. This is when time is 0. So this is your initial velocity. This is the velocity that gives the rocket, this is the rocket, I can't draw, its initial boost, and it goes up, launches up into the air. It's going pretty fast, speed at 20 seconds. There's the units in seconds. But then something happens 40 seconds later, and the velocity is 0. It's right here. Velocity is 0. That's the maximum height of the rocket, and gravity takes over. The rocket comes back down. And as it's coming down, the velocity is negative. So that's maximum height. Okay, velocity is 0. It happens when time is 40 seconds. And then 60 seconds later, it's coming towards the Earth pretty fast, negative, because the distance is decreasing. Okay, so using the results from the solution to part B, find the maximum altitude. Well, we know that the maximum height happens right here when time is 40. So if you want to find the altitude, we go to this equation and plug in t equals 40 in the original function, and f of t. So we need f of 40. So it's negative 2 times 40 cubed plus 114 times 40 squared plus 480 times 40 plus 1. So let's do that. Okay, that's not in the y equals. The y equals had the velocity. So it's negative 2 times 40. Just have to do this from scratch. Negative 2 times 40 cubed plus 114 times 40 squared plus 480 times 40 plus 1. So the maximum height of this rocket is 73,601 feet. That's pretty high up. Okay, now if you haven't flown a model rocket, might be a good thing to try out in the name of calculus. End of video.